This example shows how we can use Excel to quickly run hypothesis test for population mean using alpha or significance values provided. In this case, we are using as an example the data set of recent total pay or salaries for software engineers at Google. The source of data is Glassdoor, and as you can see, we have a column that summarizes for 50 software engineer salaries the total pay. Of course, the breakdown in base, bonus, and stock is also shown, but in this example, that doesn't matter to us, so we focus on total pay. And you can see we are talking about variance years of experience, so it's average, sort of its total pay provided different cases of years of experience. So we want to run a hypothesis test at two different levels of significance or alpha, 0.01 and 0.025, or 1%, 2.5%, we are hypothesizing that the mean total pay for software engineers at Google is at least $230,000 per year. Just as a reference from the online resources, the total pay breakdown on average is, let's say, about $230K and breakdown into 3 rows: base pay, bonus, stock, as you can see here. And we are talking about, let's say, the pay estimate for each component, average, and the most likely range, like 99% range or something like that. And the total pay percentage, for example, the last column as a reference is just saying, for instance, that on average, it is expected that about 23.2% of the total annual pay is in a stock, at least for recently for software engineers at Google. Now, with that in mind, just bear in mind that the data set that is provided here, this data set is of size 50. So n is equal to 50. Now, to focus on the running hypothesis test, which is for population mean, in this case, the total pay, let me just switch to this view in which I just show in one column the total pay. And what I need to do is first, let's form the hypotheses. So we are running, the hypothesis test with the null hypothesis, stating that the mean total pay, mu, is greater or equal $230,000 for, so the mean total pay annually for software engineers at Google currently is hypothesized to be greater or equal $230,000. So this value is mu 0 or hypothesized value. So this is mu 0 or mu naught. And of course, the alternate hypothesis or alternative hypothesis would be otherwise, meaning that no, mu is actually less than $230,000 or hypothesized value. Okay, so this is the formation of hypotheses, the two hypotheses that we have, null and alternate. Now, what do we need to do? Okay, it's obviously one-tailed scenario, and it's lower tail as shown here. This visualization is exactly showing what we are dealing with, the lower tail scenario. Okay, so what are we going to do? We're going to use the alpha. For example, the two alpha that is targeted is this one and this one. For instance, for let's say 1% or 2.5%, this dark blue area that is shown at the lower tail of the distribution, which is the probability density function or PDF, that area is alpha or significance level, which is type 1 error probability or false positive. And what we are trying to say is, let's find, for example, in critical value approach, we are saying let's find this threshold that is, I'm highlighting in light blue color, which we refer to, say, T alpha, because we have to use T or student distribution. I'm going to briefly mention. So let's find that critical value. Then let's find our test statistic, T value, and then let's compare. If T value is above this threshold, so T value greater than this T alpha, then we would say we are safe. We are at the significance level presented here. There is not enough statistical evidence to reject the null. basically, if t is above t alpha, we are dealing with this situation from p-value perspective. So this is our t-value or test statistic on the x-axis, which is the axis for the t-value or z-value if it was normal distribution, which is not. And then this critical value below which is the part that I showed above, the tail area is equal to alpha. So if we are using p-value method, then we have to find the probability associated with test statistic, and then which is the dashed area, and then compare that with significance level, which is the blue area. And if that dashed area is larger than the significance level, correspond to the fact that, or is an indication of the fact that then test statistic is greater than critical value. So we're gonna then say what I said. We're not gonna reject null. Okay, so let's proceed with this. And one last point is, why can't we use standard normal distribution? The answer is we can't. So let me see if I have enough space. So we can't use, here's the deal. I'm gonna write using different color. So we can't use standard normal distribution, or Z. Standard normal PDF, because population standard deviation, or basically sigma, is unknown. So I'm going to write on top, sigma is unknown. We don't know, it's not provided that what the standard deviation of total pay for all software engineers working at Google is. We don't know that. All we know is a standard deviation of just 50 software engineers in the data set that we have. So since because population standard deviation sigma is unknown, Okay, since it is unknown, we have to use T distribution or student distribution. And that T distribution is what I highlight here. There you go. So we can't use a standard normal, we have to use T distribution, and that is this one. So the test statistic we're going to use, so the test statistic for hypothesis test that we're going to use is this one, in which X bar is the sample mean, or basically the average coming from the data set of 50 salaries we have. Mu is the hypothesized value, in this case 230K. S is the standard deviation of the sample of the salaries in the sample we have. N is 50. And of course, S over rad N in denominator is just sigma X bar, or basically standard deviation of sample mean or standard error. So standard error. Alright, so just as an illustration, the black PDF, this is PDF plot illustration or property density function. The black one is the normal, standard normal, what we are used to. Since we don't know sigma of population, and we are using in denominator for test statistics, as you can see here, we are using S, or the sample standard deviation, as a point estimator for sigma. We needed to have sigma here. We don't have the sigma. We don't have the standard deviation of total pay for all Google engineers. What we have is the standard deviation of the limited data set we have that we can compute. So since we are doing this additional uncertainty or adding it, as a result, the PDF of the T or student distribution, which is very close to normal, sort of deviates. See, the degree of freedom DF is simply, so that for T distribution there is one additional parameter, which is DF, or degree of freedom, that is basically sample size minus 1. So just as an illustration, when sample size is pretty small, like this range, you can see that, especially this range, you can see that the T distribution deviates a lot from, in purple and blue, deviates a lot from the standard normal that is in black. But as the sample size is growing to larger sample, the delta between the t and standard normal becomes less and less. And at some point, especially when we get to sample size of 100, we can say approximately t is the same as normal. So we can use normal when sample size is above 100. But in this case, sample size is 50. So we need to stick to the t distribution. And as a result, degree of freedom, df n-1 is 49. Okay, so, and just as a reference, if you're curious about the mathematical formula behind the t distribution, all these colors, is this formula. The new, so this parameter is the degree of freedom. So okay, but we don't care about this formula. It's just a matter of for your info, FYI. Let me go back to computing what we need to compute for hypothesizing and doing a hypothesis test. So what I'm going to do is, let me just increase the size of these guys so that it's easier for you to see them. So I'm going to increase the font size to, say, these. Okay, good. Now, what I'm going to do is, I am going to, okay, make this great. All right, so sample size n is 50, obviously. Next step is computing x bar, or basically, as I said, so this one is x bar, or sample mean. And sample mean, obviously, is just simply sum of salaries or total pay, sum of total pay, divide by, for the 50 data point we have, divide by the 50. So it's just a matter of saying is equal to average. Okay, and the data set is this data, so there you go, we are done. Okay, so we got to average total annual pay for 50 Google engineers, software engineers, to be about 226,940. Okay, what is the sample standard deviation, or S? So obviously what I want to compute is now S, which is, I'm going to write it here. So S equal to S squared, or sample variance, and S is just the square root of it, is just sigma across 50 data point xi minus x bar squared divided by n-1, or 49. Okay, so I'm going to use that, but in Excel there is std standard deviation dot s of sample. There you go, standard deviation of sample that I'm going to use. And for standard deviation of sample, we're going to just run that function across this data set. So there you go. And we got to be the S, or standard deviation of sample, to be about $40,000 as we found. Now, standard error, as I highlighted, is just sigma x bar, or a standard deviation of sample mean. And that is simply the standard error, the standard deviation of sample divided by a square root of sample size, or n. There you go. So we found that the standard error for this data set of 50 data point is just about 5,700. So I'm going to write the formula in front of it so that we can just have it in mind. So sigma x bar is simply S, which is the point estimator for population standard deviation. So we don't have sigma. I wish we had it, but we don't. Divide by rad n. Okay, so the next step is now, as I mentioned earlier, I need to find critical value, for example, and t-value. This is my test statistic. So this is test statistic. And I need to find the t-value. Okay, t-value is simply, as I briefly mentioned, is just t equal to x bar minus the hypothesized value divided by the sigma x bar, which is S over rad n. So sigma x bar. Okay, so let's do that. I'm gonna just try here. So for both, I mean, it's the same value for both alpha cases. It is not different. All right, so t-value is equal to, I need x bar, which I found it here, minus the hypothesized value, which is 230k. So $230,000 and divide by sigma x bar standard error this value. Okay, so I found it to be negative 0.3, and this is applicable for both. So I'm going to copy paste formula here so that there is no confusion. It's the same thing for both scenario, and let's just stick with maybe format cell. It's a number, and let's say we're talking about maybe 4 significant digits is good enough. Okay, what is the critical value? Okay, critical value is the one, as I said here, this blue threshold is what we refer to as T alpha, or our critical value. The threshold corresponding to the dark blue area that has a dark blue range, which for which the area under the PDF curve is equal to alpha. So how do we find it? Well, best thing to do is Excel formula. So I'm going to use T distribution, see, T.DIST, and in this case, if I go with X and degree of freedom and let's say cumulate, so I need to find, in this case, I need to do the T inverse, because from alpha or probability, I want to get to the value of the T value. So T inverse, the probability, let's say, I'm going to try quickly. So let's say if I want this, it's one-tailed, and degree of freedom is n minus 1. So 50 minus 1, which is 49. Okay, so, and let me just also change the definition of cell. So format cell, it's going to be just a number for now. And let's say go with 4 decimal places. Okay, so it's trying to say it's negative, but let me see if I can just do it this way. Okay, so my formula is T dot inverse, and as I said, it's not two-tail, one-tail. The probability is this guy, and the degree of freedom is 49, 50 minus 1. Okay, great. So let's expand this to the other one as well. So I can just push this to this guy. So what are we computing? We are computing F. Okay, so great. This one need to be E2. Okay, there you go. So we found the critical value T alpha. So this one here, I'm going to use a red color so that it's highlighted. This one is T. So critical value is T alpha. This one is T 0.025, and this one is T 0.01. Okay, so great. Compare that. Compare T value to these ones as a reference, because the one that we found for the data set we have here. Now it shows we are pretty safe, because as you can see, the data set that we have, let me just make sure I'm not missing something. So what did we do? We said take the $227,000 roughly, subtract 230,000 from that, and then divide the result by 5,700. So you can see that T value is pretty safe. Is T value basically the value we have here? I'm going to use red color. So this one is T value, and this one is this blue one is T alpha. So T value, or test statistic, is definitely greater than T alpha. So we are safe for both cases. As you can see that the hypothesis test is in good shape. We are not able to reject the null hypotheses. There is not enough, or let's say at the significance levels provided here, at the alpha level values for both of them provided, there is not enough statistical evidence to be able to reject null, and we have to reject the alternative hypotheses. So reject reject the alternative and do not reject the null. Okay, so one more thing here is, if you take a look at the let's say the T table, that's also possible to be used to find the T values and or P values. That's one other method we can use to achieve that. I hope this example is helpful in terms of illustrating how we can use Excel And also the tables, if need be, aside from Excel formulas. For instance, if you're curious, we can go ahead with, say, the t values in the range of the degree of freedom in the range of 40 to 50, and then let's say if you're shooting for one tail for, say, 0.025 or 0.01, then you can see that the value of the range of values for corresponding critical values matching what we more accurately found using the Excel function. But I'm just trying to highlight that how you can potentially use t-table to find the corresponding values that you need if you don't have access to t function formula in Excel. All right, so I hope that this example is helpful in terms of illustrating how Excel can be used to quickly run a hypothesis test at given significance level. If you're interested to see the similar example, but in the sense of running it for population proportion, not population mean, meaning that what proportion of, say, total pay would be in a stock, and hypothesizing that, then there is a separate video that covers that example as well. I hope this is helpful.